The semester with Cesar Arias, who's visiting from Davis, but he's visiting Davis from Chile, where Ergen now is. So he'll tell us about Poisson thermal models and differential algebras.
All right, so thank you very much for the chance to talk here. And it's my first time here in College Station, so happy to be here. I will be talking about this Poisson sigma models and the connection with differential algebras. This is a joint work with some other people. Nicolas Boulanger, my PhD advisor, Professor Cesar, and Alexander. And it's basically all what I want to say here is based on two papers already posted on that kind. So, okay. So the idea is, let me just give you what I call a roadmap, which is really a conjecture. And it basically deals with the question of why we are doing all of this. Okay, so the goal here, what we have in mind, is try to understand basically higher spin gravity. Okay, so there is this conjecture stating that really higher spin gravity, if we think about that, about this type of theories as a second quantized theories or target space theories, it should be possible to describe it in terms of a first quantized theory based on some topological string, basically. Okay. Basically a conjecture. So you may think on some worksheet, some target space, and let's say space-time or product, or some bigger manifold container in space-time. So the idea is that here you can write some higher spin theory, some actual principle. Okay, that's the idea. There is already some proposals here, which basically write down some action of the cubic type, Chern-Simon type, and the basic ingredients of this theory are mainly, I would say, three. The first of them is just differential forms. Also, when you want to write an action, you need some type of star product that generalizes really the wedge product. Okay, and a trace. Okay.
What dimension is it? Is that any dimension?
Any dimension. There's no really critical dimension here. So the idea is that theory, based on these ingredients and this cubic action principle, contains in some branch Basilic theory. Okay. which has no action, but in this type of proposal, people already know that some sector of the theory contains really Vasiliev equations. Okay, so the idea here is that if we really believe in this conjecture, is that you can formulate a model in the worksheet, and this candidate model is really a model of the Poisson type. Okay, so this is going to be a Poisson sigma model, a supersymmetric one. I will show you a bit. So the first quantized model, a Poisson sigma model, is going to be a model in which all of the supersymmetries are gauged. Okay, that's basically the idea. So the plan of the talk, I'll give you some outline.
What do you mean by that? You have low volume supergravity?
Even here.
Well, you said gauged supersymmetry.
Yeah, this model is really two-dimensional. It contains supersymmetry.
So it has supergravity on the worksheet.
Not really, because sort of supergravity, because as I'm going to explain in a bit, this Poisson sigma model do not contain really metric, so you don't really have supergravity. So the plan of the talk is the first two points. I want to just review what a Poisson algebra is. This Poisson algebra is for functions. And then I will show that every time that you have a Poisson algebra here in this manifold, you can induce some topological model. This is what people call Poisson sigma model. Okay. Poissonic. Then I will show you that really when you have a Poisson algebra for functions, there's no really obstruction to extend it to differential Poisson algebras. Where now you can define a bracket for differential forms of arbitrary degree. Okay, this is for forms. Okay, so when you do that, you can define this algebra for differential forms, and then one realize that the Poissonic model can be extended by fermions, and you can really write down a theory with supersymmetry. Okay, that's what we call differential Poisson sigma models. Okay, so that's basically the plan. Right? Any question?
How does it happen that it seems as if you're going to define some tools for us and formalism. So is it in any way obvious that Vasiliev theory is going to come out of that?
No, it's not obvious. We are really far from here. This is just a conjecture. Okay. So the very first step is to study this type of models, which is what we are doing now. But then
are they singled out because of some reason, or?
Sorry?
I mean, why should one study those models? Are they singled out? That there's some uniqueness statement? I mean, that do things have to happen? Or?
No, I mean, these models are really the candidates for a first quantized description of the various videos. That's yeah. There's no really, we're really far from that. It's just a conjecture thing.
But is there some reason that the Poisson sigma model, the Poisson structure is related to star product or something? Like,
yeah, I will explain that. And there's evidence, I mean, already in the Poissonic case, when you quantize this type of models, then you get really Kontsevich star product from you. Okay. I will explain this. All right, so let me define what is a Poisson manifold or a Poisson algebra. Okay? So Poisson algebra is simply a map for the space functions, smooth functions. Space of smooth functions. So that to every pair of functions, f and g, let's say, you can write down a bracket this way. It's just a typical Poisson bracket. Where now you really consider a non-invertible object, call it Poisson structure, which is only a function of the coordinates. Okay, so we can check, and in that, of course, there's some properties of this bracket. So this bracket is a bilinear bracket, meaning that you can really check this. It's anti-symmetric, and of course, there is sort of a Leibniz rule for this bracket. And also, as a every good bracket, it fulfills Jacobi's identities. Okay. Just write down this. Okay. So the first non-trivial constraint of this is the form of the Jacobis. And actually this, if you plug the definition of the bracket, this, let's assume this definition, then you can actually reduce that Jacobis implies that the Poisson by vector cannot be anything, but it should be constrained such that this identity holds. Okay? So every time you have a Poisson algebra, Jacobis identity implies this constraint. Right?
So the other one is delta.
Sorry, yeah. Right, so this is what people call Poisson condition. Alright? Good, fair enough. There's a manifold, you can dot it with a Poisson algebra, and then you can actually construct a model in which the Poisson by vector plays the role of the Hamiltonian. Okay? So now we land with what people call Poisson sigma models. This is due to Ikea, the 90s, I think, Schaller and Stroh. Okay? They realize that every time you have a Poisson structure on a manifold, you can actually write down an action of the type, of the Hamiltonian type. Where where the Poisson by vector is really the coupling of two one forms. Okay, so it should tell you what it is. this eta is a one kind of momentum, you know. Phi are coordinates on a multiple m. Okay, and then here the Poisson by vector is only a function of the coordinates. Okay, it's of course anticipated. Right? So this is. So you can actually write down this action, and then, of course, it contains some symmetries. There is a gauge symmetry here. It's a gauge symmetry that looks like this. Right? Where epsilon is some zero form parameter. And then transformation from the momentum. So it looks like that. Okay, we can easily check that this transformation leaves the action invariant. Moreover, you have hidden symmetries also, hidden type of symmetry. Meaning that for every vector that leaves the Poisson by vector invariant, you can define actually transformations for the fields. That's right. I would use the same name for the parameter, but it's a different one. Where now, of course, the indices are for the Chilean symmetries, okay? And of course, they form an algebra, meaning that the Lie derivative, this guy is really, okay? So every time you have a vector, okay, let's say, that leaves the Poisson by vector invariant, you can actually implement the symmetry. Okay. That can be for these symmetries can for the big H. Okay, so that's what people do sometimes in these models. With no obstructions. So the important thing is that besides the symmetry, the equation of motions that arrive from this action are actually forming some kind of integral system. You can check that equation of motions. Let me call the first equation of motion, I will call it just R. The second one. We can actually check that this equation of motions are integrable, and that furthermore, if you impose integrability, you will arrive to some constraint the Poisson vector, which is precisely the Poisson condition. Okay?
Or do you get the second equation of law? It's like,
Sorry?
I think I understand the first one.
Sorry, the second one is just a mistake.
But the phi equation of law?
Yes. Sorry?
That's the phi equation.
Yeah, if I
Oh, okay.
vary with respect to phi, I get the two-form equation.
Oh, okay.
This one.
So, you say that this pi can depend on phi?
Yeah, only on phi.
Okay,
This is
all right.
the dependence. Okay? So, if we impose integrability, meaning just take the exterior derivative of those equations, in this case, you arrive to the first non-trivial fact that really impose 0. That the Poisson vector is really constrained. Okay? And the constraint is precisely the constraint coming from the Jacobi's identity in the algebra side. Okay? So this is already non-trivial. People notice this when
You also need that for the gauge variance, don't you?
this condition. Yes, it's also needed. And then if you do the same with the two-form equation of motion, then you just take the derivative of this equation. Okay, but as I said, the first non-trivial fact is that you can state it like something like integrability of the model. So the Poisson simple model is equivalent to that the Poisson algebra fulfill Jacobi's identity. Okay? So on the one hand, you had an algebra that already imposes constraints on the Poisson manifold, and on the other hand, you have a model that really, when you demand integrability, you get the same condition. Okay?
So there's another way to say that this action function only makes sense if the target is truly a Poisson.
Right, exactly. And that's what people, I mean, it was first noticed that you can induce, this is really an induced model in that sense. Okay? Every Poisson structure is inducing really this kind of model, right? So now, of course, you can ask, okay, this is Poissonic, and the algebra is really for functions. So the natural question is whether if you can extend this type of algebras as to admit differential forms or of arbitrary degree. And you can also ask, well, if you do that, then is there any model in which the Jacobis of this algebra really correspond to the integrability of this model? And the answer is yes. You can extend the algebra of functions, and then you can also extend the model as to admit fermions. And then you compute, and you realize that, as in the Poissonic case, you can actually achieve integrability by demanding that the differential Poisson algebra fulfill Jacobi's identity.
Are you going to explain the relationship between differential forms and higher spin? Differential forms usually don't have anything to do with higher spin.
No. I mean, I'm only going to talk about these models, but I'm not going to touch anything about higher spins. So that's the very first motivation, but it's not really clear what we're going to do there.
And if pi is invertible, then it's topological?
I mean, pi is not invertible here.
If it were, well, why are you using the fact that it's not invertible? It's allowed to be non-invertible, but it doesn't have to be non-invertible, right?
It doesn't have to be, but then you don't have Poisson stuff. The Poisson algebra is realized for Poisson, for non-invertible Poisson structures.
But why is being invertible an issue?
Sorry?
Why is it important, being invertible or non-invertible? So what happens if it is invertible?
Well, the model wouldn't be topological.
Not clear.
If it's invertible, you can gauge away phi completely. Right? So then you have no propagating degrees of freedom.
Right. Sorry.
So I think you want it to be non-invertible so that you have something, but because otherwise you can gauge away your field. But I don't think you used it anywhere when you defined the Poisson structure.
Well, here, kind of. I mean, if pi were invertible, then just the derivative would be zero.
Including this constant.
Well, then I want to conclude that pi is closed as a differential form of degree 2, which is the correct statement, right? Because it's a symplectic form.
Okay. Yes.
But
But what if you just have a Poisson bracket? I mean, just plain classical mechanics Poisson bracket, isn't that invertible?
it is, but
It
it's
is.
also identically satisfied because
It satisfies that. So and then your model doesn't make sense. Or
oh, then you could gauge away phi.
then you have the model.
Then you have no local degrees of freedom.
Oh, okay.
in the world. That's why I was asking whether it's topological.
So let me just comment on, you were also asking at the beginning. It turns out that you can quantize this model in a perturbative way. Actually, it was done by and Felder in the 90s also. And they show that when you quantize this model, in a HET fashion, then every term in the expansion can be really associated with every term in the Kontsevich star product. Okay. Which is basically, I will tell you immediately, what Kontsevich is that you can really deform the classical product of two functions, f and g, and you can deform it in terms of expansion in h bar. And really the first term, the first order in h bar is really the Poisson bracket. And the rest is just higher order in h. Okay. So what these people did, Cataneo and Felder, show that when you quantize the model, you really reobtain Kontsevich formula. Okay. So that would be the second non-trivial fact.
What do you mean by quantizing the model? Canonical quantization or?
No, HET. You introduce ghost and superfields.
Path integral.
Sorry?
Path integral.
Yes, path integral. Okay. So the second non-trivial statement about this kind of models is that it gives you a second way to quantize a Poisson manifold. Okay. In the sense that this program here is called information quantization. So you can state that there are two ways of quantize really a Poisson manifold. Okay. You can quantize it either a la Kontsevich with using star product, or you can really quantize this Poisson sigma model. Okay. Both agree. Okay. that's already a nice fact.
Can you say what's the relation between the Kutsevich star product and the Moyal product? Like they are
Yeah, I mean,
equivalent in special cases?
Yeah, Moyal is when you take the limit. I mean, if you do Kutsevich product on Rn,
Yeah.
then you get Moyal.
Okay.
That's true. Important point. Okay, so all of that is kind of, everything is done. People have been studying this model for a while.
On R2N, right?
Sorry?
Yeah.
R2N. Or
Sorry,
whatever.
2 and yes, should be easy. Yep. So okay, now we are back to the question of whether can you generalize this really to more general type of models like the neural. In the very first step is to define an algebra, but now for differential forms. This is what people call differential Poisson algebras. There's also, it was done by some people, if I remember correctly, was HET, X, and also Sumino. Okay, so you can actually just generalize the rules, right, and then define some bracket, which just tell you what it is.
Your world sheet is always 2-inch.
Yeah, always 2D.
Okay.
Yeah, so it's better if I just write the bracket and just tell you what it is. Okay, so if you consider two differential forms of arbitrary degree, the first part is kind of obvious. But if you do it in the systematic way, you won't realize that we should really introduce connections. Okay, so these derivatives are really something like that. And since you are introducing a connection, it would naturally appear a second term, which depend on those connections also. Maybe some grading. Okay, so this guy here is the derivative form associated with a second connection. Okay. Gamma tilde, which is related to the first connection line, simply by the torsion. Okay. So actually, you can endow the manifold M with this type of algebras for differential forms. And now you can ask whether is there any theory, topological theory, which really has target space endowed with this algebra. Okay.
Are those indices wrong? Should be the gamma beta on the second one?
Yeah, sorry. So this is just telling me that you have torsion.
And is there any compatibility condition on this connection with the Poisson structure?
Yeah, there is a compatibility condition. You impose. I forgot to say that.
Sorry. R is the curvature of gamma.
Yes. Gamma
You
T.
wrote R equals gamma.
No, sorry. It's constructed. Yeah. Okay. So there is a systematic way to do this, and then you have to impose this compatibility language. Okay. Then you do the systematics, and then you land to this kind of algebra.
Is it unique, like metric compatibility? I mean,
There's no metric here. This is kind of looks like
yeah.
the metric compatibility, right?
But are there, do you get a unique connection? Like, is there an analog of what needs to be done?
No, I mean here, you don't need, I mean there's no need for unique connection. Actually, you introduce two connections
Okay.
in order to be able to construct this, this bracket. Okay. Okay, so let me just tell you that
So the action on differential forms is just slot-wise. You just go through all the slots and put in gamma. Sorry? I want to know what the action of gamma on a differential form is. Just contract the upper index on each index consecutively.
I mean, this is a one form, so you have to wait that.
Gamma.
Gamma is a one form. It's a one form connection.
Sure, but it's valued in automorphisms of one forms, and you're acting on. I guess you just extend by linearity.
So you can also, in the same way that people did it for the Poissonic case, in the algebra of functions, you can cook up an action where now the target space of this theory will be endowed with that algebra of differential. Okay? Let me just write what the theory is. Contain the Poissonic part. It also now contains fermions. So I will just introduce two fermions. Let's say coordinate. I'm just going to extend it by some degree 1, Fermi degree 1 object, and then the one form also have this fermionic part. Okay. So now I can just write here kinetic term fermions. This. And since I'm introducing connections, it will naturally appear a quartic coupling, which looks like this. Okay. So now you have fermions, and then you really have a theory which has more symmetry, in particular has supersymmetry. Okay. So let me just write here a small table to name what is everything. So you will have two zero forms, theta and phi. But one of them is now a fermion. Okay, meaning that has all the statistics. Okay. And then the same thing for the momenta. You have a Poissonic one form, which is eta, and the inner one. And then you introduce a fermionic one form. Okay. Those are the field content.
Just to make sure I understand, R tilde is symmetric?
Sorry?
R tilde is symmetric?
Yes, it's symmetric.
Okay.
And, this indices. Because, I mean, depend on I mean, these are one forms.
No, it would have to be symmetric in one and anti-symmetric in the other if you're contracted with big squared.
Yeah, yeah, sorry. It is,
Because
Yeah,
the
this-
chi squared would be symmetric. Because they're fermionic one forms.
yeah, this is antisymmetric. And those are symmetric, because I'm considering really dimension of the total degree. So, I mean, chi is effectively a Poisson, because it's a fermionic one form.
Dumb question. So, it's one form on the roller sheet, right?
In the target.
In the target.
Yes. Here I really have to pull back everything, right? Like the sigma model now.
Okay. I see.
Okay, so you have this model. You have a
Sorry, why is this bracket graded anti-symmetric? Is that clear? R is symmetric.
yeah. I mean, the bracket is really skew symmetric.
Oh, there's a wedge.
Yeah, there's a wedge here.
No, I mean, I'm talking about the other one.
Yes. Yeah, it should be more careful with this one.
So if omega and eta are one forms, then the last term is just R contracted on two
Yes. Yeah.
vectors, but then it's not anti-symmetric, is it?
Degree of omega.
Oh, sorry, now it has to be symmetric, okay.
Okay, so you have this theory now, whose target space is really endowed with a differential Poisson algebra. You have gauge symmetry. I'm just not going to write everything. I just want to make a point here that, as in the Poissonic case, you can impose integrability of this model. It turns out to be equivalent that this bracket fulfills Jacobi's identities. Okay. Okay. This is also kind of non-trivial fact. And I can list for you what are those integrability conditions are. The first one is really just the Poissonic. And then you have constraints on the curvature. And so on. Okay, so now since you introduce connections and all of that, then you will have a bunch of constraints coming either from the integrability of the model regarding the equation of motion of this action, or imposing the Jacobi's identity for this bracket. Okay?
Should that expression, one of those, should that be the last index on R be upstairs? Is it the forward? I'm confused.
Sorry?
Sorry, the
raising
middle
lower
two
units.
expressions, the
Oh
R.
yeah, so sorry. I'm calling. Sorry about that. And basically this. I want to write this. Yeah, I should say here. This guy is really delta beta. Sorry.
So the R natively has 3 down, 1 up, and then you raise 1
If you have too
above.
many
That one
values.
should have been
Right, that one
down,
should have
up,
been-
and then
Not
you
too
raised
many
one on
down
that
in
one.
this
Yeah,
is-
yeah.
Okay. Just denoting indices, right? All right, so that's the analog with the bosonic case, but now you have
What's the point of the torsion? I mean, is it just because you can, or is it not interesting if you don't?
I mean, if you don't have torsion, you see what happened here. This is identically fulfilled. So,
That's too easy?
sorry?
That's too easy or not interesting?
I mean, you need to introduce torsion because otherwise you cannot really write down a bracket. That's the point.
So you have to have that R tilde.
Yes. I need 2 connections and I need to have torsion. Otherwise I cannot just write down a bracket for differential forms.
And then since we have torsion, even back in the function case, shouldn't we have really introduced that connection because covariant derivatives would commute even on functions?
I mean, they're functions, right? So
Yeah, but
you don't really.
I thought that the actual covariant derivatives on functions only commuted when it was torsion. Or is that, am I getting that wrong?
Say again.
Current derivatives commute on functions because.
Because they're torsion free.
Yeah. If there's torsion, their algebra will give you torsion times a derivative.
Yeah, so but even back when we were talking about the ordinary Poisson sigma models, we should have had connections, not just ordinary derivatives.
Well, everything he had.
But that's okay, we can talk about that after.
So since we introduce really fermions, we can ask somehow that you have supersymmetry, right? And it turns out that this supersymmetry is really, if you want to translate it to the algebra side, is really the compatibility of the bracket with the Durand differential, okay? So you can think secretly about the compatibility. Okay, so this supersymmetry is really important. All right, so I can tell you that.
So what's D? D is exterior derivative?
Yeah, Durand. Okay, so you just promote these transformations, one can note that reaction is invariant. Symmetry is really supersymmetries. One can write the whole theory in a kind of vectoric superspace, and then the symmetries are really trivial. Okay, or manifest. Just want to show you that the action contains this supersymmetry, and this supersymmetry, if you think on the target space, it's really the compatibility with the Durand differential. Okay. You really have this group. Okay. Any question? Okay, so now.
So there's nice superspace. version of that? The thing you just erased, is there a compact superspace?
Yes, there is just two terms action in superspace. I don't think I will have time to. Yeah, and then you can easily write out this supersymmetries in terms of.
So in the bosonic sigma Poisson business, then the Hilbert spaces naturally see smooth functions on M. Right? And now here, I guess, just like with Witten's paper on Morse theory, because you introduced worldsheet fermionic one forms, when you quantize this system, you're going to get differential forms.
Yes.
In the target.
Yes. That's another way to say that if you think about differential forms on target space, you can ask, how can I pull back something to the worldsheet? Then the answer is just introduce a fermionic 0 form. So that plays the role of D5. All right. So the last comment. The last comment is, of course, quantization, right? You can ask whether it's possible to quantize this model. The answer is yes, you can do it. But in order to do that, you really need to do the superspace formulation, okay? Because it's more simple. And then when you quantize the model, you can presumably, this is something that we haven't done, but presumably you can extend really the Korsevich formula, star product, to differential forms. Okay, so presumably you can just there should exist some deformation of the classical wedge product, where the first term is something like the Poisson bracket I just wrote, plus eigenborders. Okay, so that would be nice. This is the second one, 4. Okay. So the usage of the fermionic model. Sorry, non-fact.
Non-fact. Well, we're in alternative fact.
Yeah, I did it before. Yeah, so the idea now is, this is what we're trying to do now, is that quantize the model, you can somehow extend the Korsevich star product in this fashion. Okay. And I think I'm going to stop here. Basically what I wanted to show.
Any more questions? So the nice thing here is that essentially you know that this will happen because of essentially because of Witten's work.
This is what we do?
So when Witten did it for supersymmetry to Morse theory, but there the RNS fermions become, or in topological strings, the RNS fermions become the one forms in the target space.
Yes.
The basis one forms.
That's true.
So here you're using, it's not as, yeah, so here you're doing the same thing, I guess, with theta. Right?
Yeah.
So because it worked before, now it'll work again because everything is now, instead of a function, it's a function valued in forms, which is what the Hilbert space of that system will be.
Exactly. That's the